the efforts we are doing in the Kernel Self-Protection Project. The Kernel Self-Protection Project is a project within the Linux kernel community. And what we do, we work on proactive security, which means that we are trying to harden the Linux kernel. We are trying to prevent vulnerabilities from happening in the kernel, right? And well, just a little bit about me. Of course, I am a proud student of the University of Adelaide. I've been doing this work, working as an upstream Linux kernel engineer for 9 years now. And well, as I said, I focus on kernel hardening and proactive security. The Kernel Self-Protection Project, I am a member of this project, and this project is basically the Linux kernel division of the Google open source security team. And well, this is the agenda for today. Let me ask you a couple of questions. So do you have some experience with the C language? You all have some experience with the C language? Okay, great. Yeah, because this is all about C, of course. And this presentation is going to be very, very technical. So usually, my audience usually are Linux kernel maintainers. And well, we didn't have time to prepare a different presentation, so I had this ready. So this is what I'm going to give you. I don't think there is a problem if you don't have much experience programming in C. Probably this is a very good introduction for you to know a lot of the things that you can do with the language, and sort of like the state of art of some of the hardening options and hardening attributes that some compilers like GCC and Clang have right now. So yeah, so we are going to start with some very basic stuff, explaining what is an array, the most simple declaration of an array in the C language. I'm going to explain a little bit about what is this thing, flexible arrays, what are flexible arrays, what are flexible structures. I'm going to explain a little bit about the work of flexible array transformations that we have been doing in the kernel for years. And of course, then we are going to jump to the main part of the presentation, where I'm going to be explaining to you how it is that we are hardening our own version of memcpy. Because, well, in the kernel, we have our own memcpy functions and our functions to handle strings. And this fstrict-flex-arrays is a recent compiler option that you can use to harden any C code base out there, not necessarily only the Linux kernel, right? So if you have your own pet project or you are working on your own C project, you can use all of these options and attributes that I'm going to show to you. And well, at the end, of course, some conclusions. Okay, so well, this is probably the most simple declaration of an array in the C language. What we have here is, well, a fixed size array. And something important to notice here, and something that is important for the rest of the presentation, is to distinguish clearly when the compiler can determine the size of this object at build time, right? So in this case, the compiler has all the information it needs to determine exactly the size of this object at build time, right? So the size of this object is going to be 10 elements of type int, right? So whatever it is the architecture we are working on, that is going to be the size of this flexible array. I mean, if we are working in a 32-bit architecture, or we are working on a 16-bit architecture, of course, the size of the integer is going to be different, right? Okay, well, before I move on, something important to mention here is that usually when we use arrays in the C language, the developers are in charge of taking care of not writing or reading beyond the boundaries of these arrays, right? So the C language doesn't enforce out-of-bounds checking, right? It is up to the developers to take care of that, right? Okay, now let's explain a little bit about what is this thing, trailing arrays. Okay, a trailing array is merely an array that is going to be declared at the end of a structure, right? So in this case, we have struct foo, just struct whatever, and we have some members, and at the end, the last member, if the last member of the structure is an array, we are going to say that is a trailing array, right? Okay, and again, the size of this trailing array is clearly well defined at compile time. I'm repeating this because this is important for the rest of the presentation. Now, a flexible structure. Well, sometimes there are going to be a lot of cases we are going to run into all sorts of situations where we need to use an array in a structure, but at compile time, we don't really know how big this array is going to be, right? The size of this array is only going to be determined dynamically, right? So we need to execute our code, and then we are going to, we need to allocate some heap space, and then is when we are going to know how big or how large this array is going to be. So in this case, this is an example of a flexible array. The declaration of a flexible array is merely with empty square brackets. So you don't use a concrete size. And a flexible structure is a structure that contains a flexible array, right? And that flexible array should always be at the end. And so yeah, again, what I just said, we use one of these types of objects when we don't know how big the array is going to be at build time. Okay, the right technical term for flexible arrays is actually flexible array members. These type of objects were introduced to the C language in C99. However, we have started using these arrays recently in the Linux kernel. So yeah, it's a proper way, it's the right proper way, the right technical way to declare an object which size is going to be dynamically determined at runtime. Some of you might be wondering, okay, well, but before C99, people had the need to use this kind of objects, right? They needed to declare an object that can be variable in size at runtime. So for that, people would use one-element arrays or zero-length arrays. So instead of the empty brackets, people would declare an array of one element, just one there, or zero, right? In the case of zero, well, the first option that people used was the one-element arrays. Zero-length arrays are not actually part of the language. It's not zero-length array is not actually part of the C standard. Zero-length arrays were introduced by compilers as an extension to the language. And the reason why they introduced this is actually to try to remediate the problems that using one-element arrays were causing in C code bases, right? And well, the problems they were causing when they were declared as a one-element array, but in reality at runtime they were used as variable length objects. And well, when we need to use a flexible array, and of course a flexible structure, it is usually the case that we need to add another member in the flexible structure that we are going to use as the counter member. In this case, the counter member is useful for us to store the total number of items or elements this flexible array is going to contain at runtime, right? So that's that's like a helper variable, a helper member. So whenever we need to allocate a certain amount of heap space for the flexible array, we are going to store in this counter member how many elements this flexible array contains at runtime, right? And of course, we use this variable to iterate over the array and to not go outbounds this array, right? To don't write beyond the boundaries of the array or to not read from beyond the boundaries of this flexible array. And this is an example of how we use a flexible structure and a flexible array in the Linux kernel. What we have here is, what we are doing here is actually we are calculating the total size for both the flexible structure and a number of items for the flexible array. So in this case, this items variable is a variable that contains the number of items that we are going to allocate for this flexible array. And this is usually how people calculate the size. So what we have here is basically we are getting the size of the flexible structure, And we are also calculating the number of elements the array is going to have, and we are getting here the size of the flexible array. So this part, size of struct foo plus items, is actually the size, the total size of the flexible array, right? So, and then we add this to the size of the flexible structure, and now we have enough heap space for the flexible structure with all its elements, with all its members, plus a certain size for the flexible array, right? And well, here at the bottom, you can see how we are updating the counter variable with the number of elements we actually allocated for the flexible array. In the kernel, we don't like this kind of open-coded arithmetic because those are usually prone to problems when it comes to allocating heap space, right? We can actually we can run into in the case where we are actually trying to allocate more space than needed. Well, actually, what this could happen is an integer overflow, actually. But what could happen here is that we can run into an integer overflow, and then we run into all sorts of issues when it comes to allocating the heap space. So that is the reason why we don't use open-coded arithmetic. For the kernel, we have all sorts of helpers. In this case, the helper that we use to calculate the size of a flexible structure and a flexible array member is struct size. So that helper is the one that we use. And well, actually, a few years ago, probably 6 years ago, I was looking for this open-coded arithmetic in the kernel and replacing this with struct size, trying to prevent some integer overflows while allocating heap space. And then I run into this issue. What we have here is a structure that contains a zero-length array. This is actually the patch that introduced the bug that I'm going to explain. What we have here is this person introduced a new member to the flexible structure just after the zero-length array. The problem here was that zero-length array at runtime was being used as a flexible array member. So what happens here is that people were allocating certain heap space for this zero-length array, because they wanted to use it as a flexible array member. And at the moment they write some data into this array, they were corrupting this RCU head member, right? So that's a bug. That's actually undefined behavior for the C language and for compilers. And that's a bug, that's an issue. And well, the way in which we fix this is, well, one simple way to fix this problem is, okay, well, the zero-length array was at the bottom, at the end of the structure. Okay, just put it again at the end of the structure and leave it at this, and that's fine. Yeah, that's a solution. But actually the best solution is, place that flexible array, that zero-length array, at the bottom of the flexible structure, and replace it with an actual flexible array member. Okay, now, when the compiler sees this code and detects that someone is trying to add a new member to this structure after a flexible array member, now the compiler is going to complain, because that is some of the requirements to use flexible array members, that they have to be at the end of the structure, right? So in this case, if we transform this zero-length array into a flexible array member, now the compiler is going to help us to detect this kind of undefined behavior bugs, right? And that is something useful, because we need to, what we are trying to do in the Kernel Self-Protection Project is we are trying to use as much as possible all the infrastructure compilers, modern compilers already have to harden C code bases, right? So I don't know if you are a freshman or if you are doing a master's degree, but if you have a few experience coding in the C language, this information is pretty useful for you, because what I want to transmit to you is that use the compiler. The compiler is your friend, right? Don't try to lie to the compiler. Don't try to write code that is ambiguous to the compiler, right? Because that is prone to error. and that opens the door for the introduction of all sorts of issues. Okay, so this is the interesting part. Yeah, this bug was there in the kernel for 8 years. It was introduced in 2011, and I discovered it in 2019. So unfortunately, I have to say that I'm pretty sure that there are more bugs like this in the kernel, years old bugs that we haven't discovered yet. Okay, so well, this when we discovered this bug, we were like, okay, this is actually a problem. We have a problem here. People are using one-element arrays and zero-length arrays as a way to declare a flexible array member. They are lying to the compiler. The compiler is not able to do anything about it. So we need to fix this issue. So the next thing that we did was we went and looked for all the instances of zero-length arrays and one-element arrays that were being used as flexible array members across the whole kernel tree. And we started to replace those with actual C99 flexible array members, right? So that the compiler could help us to detect these issues. And probably it might seem, I don't know if this seems simple to you or not, but that work took us like probably between 5 and 6 years to do. It's quite simple to replace a zero-length array with a C99 flexible array member, because at the end of the day, the size of this object for the compiler is 0. This means that if there are some instances of code in the kernel that are using something like size of struct L2T data, the size of that code construct is not going to change, right? Because it's the same with a zero-length array or with a flexible array member. However, in the case of one-element arrays, if we replace a one-element array with a C99 flexible array member, now the size of the flexible structure changes. And that is really problematic, because there are a lot of places in the code where people are going to use the size of the structure. They are going to apply the size of operator to the structure to do all sorts of computations and calculations, right? So the thing that we had to do at the time was, okay, we replaced the zero-length, the one-element array with a C99 flexible array member. Now we need to go and look for all those instances of code across the whole kernel tree, across all sorts of drivers and code, and look for all those instances that were applying the size of operator to the flexible structure, and try to compensate for that change in the size of the flexible structure. And that's really problematic. And we had to refactor a lot of code, and we had to do all sorts of things in order to accommodate for this simple change. And that is usually the case in the kernel. And more so when it comes to trying to harden the Linux kernel. Because usually what happens is that we identify a class of bug, a class of vulnerability, a class of issue, and then we want to fix this instance across the whole kernel tree, and then we run into more problems, right? Because maintainers, they are fine if you send code to fix their issues, as long as your code is complete, let's say, right? As long as you do whatever is needed in order to refactor the code, the whole code, and leave it in a sane state, let's say, right? So in the Kernel Self-Protection Project, we allocate that pain. We cannot just simply make this change and say, well, you know what? You need to use a C99 flexible array member. We just replace the one-element array with a C99 flexible array member. Now is your turn, is your responsibility to fix your code. That is not the case in kernel, in upstream Linux kernel development. The people that is proposing the change, the people that wants their changes to be applied to all sorts of subsystems in the kernel, those people are in charge of doing all the work that is needed in order to leave the code in a good state, right? And that is a lot of work. And well, the reason I'm telling you all this story is because well, this is not a usual presentation. I mean, Again, I usually present, my audience usually is Linux kernel maintainers, so they know all this, right? But I'm giving you this because, well, you are probably you are interested in the kernel. I'm giving you this as an advice, right? And that's the reason why I'm extending in this part. And well, let's move on. Okay, well, let's jump to the main part of the presentation. This that I just presented is the most simple thing, the most basic thing for kernel developers, right? To understand and to grasp. They have mastered this. Now we are going to jump into very, very, very technical stuff. But don't worry, you can ask me any question, and hopefully I have an answer for that. Okay, well, back in 2020, I don't know if you are aware of the bleeding tooth vulnerabilities. Have you heard about it? No? Okay, well, this is the story. Back in 2020, this security researcher at Google, he discovered 3 vulnerabilities that he decided to call them the bleeding tooth vulnerabilities. The bleeding tooth vulnerabilities. The reason for that is because, well, he discovered those in Bluetooth code, right? In the Bluetooth subsystem. This one that we have here is one of them, is the bad vibes. Bad vibes, okay, what is going on here? This person discovered that there was this array in the middle of a structure. And then on this other side, we have a main copy. And what is going on here is that, well, we are actually, we are writing some data of certain length into this array, right? It's quite simple. However, if you notice here, the array has a concrete size at compile time, is 31 bytes. However, at the moment of writing certain data into this array, we are not sanity checking. We are not checking the length. We are not checking how many bytes we are going to write into this array. You see? Len is the variable. Len holds the number of bytes we want to write into the array. And there is no code checking for how many bytes we are about to write into this array. You see? That is an issue already. Even when this code is not exploitable or nothing happens, and this len is always less than 31 bytes, that in itself is an issue. It's a bad security code in practice. Okay, so that's what I just said. Len was not being sanity checked. That is usually not great. And well, this security researcher, he was speculating about the possibility of overriding this array, and actually he wanted to corrupt this next pointer. That was his objective. And the thing is that he did it. he managed to corrupt this array, and he managed to corrupt this pointer, and yeah, that was the problem. That was the issue. Okay. So what is the problem? Well, this begs the question, what is the problem with APIs like memcpy in this case? In this case, we can say that API is a pretty naive API, right? Because it is trusting you, right? It is trusting on us as developers, right? But we make all sorts of mistakes all the time. Okay, so yeah, I mean, memcpy doesn't really know your true intentions. It's a pretty naive vulnerability. And again, it's similarly to the case of just an array in the C language. Developers have to be in charge. We are in charge of enforcing the boundaries, in this case, of both the source and the destination objects. And we need to make sure that we are not reading beyond the boundaries of the source object, and we are not writing beyond the boundaries of the destination object. Right. Okay, so bad bytes was fixed at the time. So what do you think was the fix for bad vibes? Can you imagine?
Wouldn't just be like a sanity check before memcpy?
Right. I mean that's sensible, right? Yeah. Actually, that was the fix at the time. They just, with this simple couple of lines of code, yeah, I mean, the moment they detect we want to write more bytes than our array can hold, well, we just return it. Yeah, we don't execute the memcpy function, right? Okay, yeah, that was the fix. However, it'd be great if we don't have to trust on developers. It'd be great if memcpy, it'd be great if we can modify memcpy so that internally we can sanity check that length, right, that size, and make sure that we never are going to write or read beyond the boundaries of source and destination objects, right? And this is actually the intention of the fortified version of memcpy. We have our fortified version of memcpy. When you build a Linux kernel, you can build it under certain, you can enable certain flags, and with that you are telling the kernel, okay, I don't want the regular memcpy. I want my system to be a little bit more secure. So please enable the fortified version of memcpy. Okay, so this is a simplification of the fortified version of memcpy we had at the time before bad vibes. So this is a simplification. If you go and take a look at the kernel, you are going to see a much larger function. But for the purpose of the presentation, let's go with this. Okay, so the workhorse of a fortified version of memcpy is building object size. Building object size is a built-in compiler function. So do you know what that is? Okay, well, a built-in compiler function is not a function that is defined and implemented in the kernel. Those are functions, those are APIs the compiler provides for developers, right? So if you are using GCC or Clang, you can write the most simple main function in the C language, and you are already able to call this built-in compiler function because the compiler provides this function, right? Okay, so this is one of those. Okay, with this function, the intention is to, what this built-in function does is that we are going to pass a pointer to an object, and it is going to return the size of the object this pointer is pointing to, right? That is its functionality. So in this case, we were calling building object size, and we were saying, okay, well, you know what? We need, if possible, if you can give me the size of destination, please give it to me, and I'm going to store it in this local destination size variable, right? And the same with the source object. So we are telling the compiler to give us this information because in the case, let's remember our most simple declaration of an array in the C language, an array with a concrete size, the compiler knows exactly, and is going to know during the whole lifetime of our program, the compiler is going to have access to that information, right? So we can ask for that information at any time. Okay. So this is the other part. Okay, what we say, okay, the compiler, we ask for the size of the objects. This is another built-in compiler function. We just check if this size is a built-time constant, right? If the size in this variable, if we have a complete size stored in this variable, right? And then we check the size against the size of destination object and against the size of source object. And well, if the size of, if the number of bytes we want to write into destination size is larger than the actual size of the object, we call this function and we say, you know what, we have a write overflow here, right? And it's the same case for when you want to write, when you want to read beyond the boundaries of the source object, right? Is not that hard to get. And this is this part was for compile time. This is for runtime, right? But it's basically the same idea. And well, at the end, if everything is right, if we don't detect any write overflow or any read overflow, well, we execute the memcpy because we have determined that it's safe to execute, right? Okay, so yeah, so this is what we had before bad vibes, and okay, so I'm going to explain I'm going to explain a little bit of the internals of this built-in compiler function. But at the time, this security researcher, he, if I remember correctly, he didn't, he found this vulnerability, but the kernel he used didn't have the 45 version of memcpy enabled. But we're about to see why that, I mean, it doesn't make any difference. Okay, let's see, let me explain you a little bit how this building compiler function works. Okay, we can use this building compiler function in two different modes. There are actually four, but for this presentation, we are going to focus on two because those are the ones that we use in the kernel. So if you remember, we are passing a pointer to a destination object and to a source object, and we are passing a 0 here. That is a mode we are going to use. In mode 0, it says if we pass here 0, this building compiler function is going to return the size of the object from the beginning of the object up to the end of any containing structure. So it is not returning the actual size of the object. It's returning more than that. But if we use mode 1, it is going to return the actual size of the object. Now, let's see some examples. We have here a flexible structure, and let's assume the size of our integer is going to be 4 bytes. We have an array of 8 bytes. We have another member. We have another 4 bytes, and we have a flexible array member. Okay. Let's compare what this building compiler function returns in both in mode 0 and in mode 1. Okay, in mode 0, it returns 16. Why is this returning 16? Because 16 is the number of bytes from the beginning of this object up to the end of the structure, right? Okay, and in the case of mode 1, it is going to return the actual size of the object. So it's precise, more precise. In the case of the array, it's going to return 12 because that is the size from the beginning of the object name to the end of the structure. And of course, in the case of mode 1, it's going to return 8 bytes. In the same case, well, now this is where it is getting even more interesting. In the case of a flexible array is an object of incomplete type. If you don't know, the type of the object is composed from both let's say the identifier for the type, but it is also composed of the size of the object. I'm sorry. So in this case, this object lacks a size. It only informs the compiler that whatever the size this object is going to be at runtime, okay, the type of every one of those elements or items is going to be char. I'm sorry, I haven't mastered this pronunciation yet. But yeah, when we pass a pointer to this building object size compiler function to an object of incomplete type, regardless of the mode we use, this function is going to say, you know what? You are passing me a pointer to an object of incomplete type, so I'm not able to determine the size of this object. So I don't know, and have -1, right? Okay, so let's go back to the bad bytes vulnerability. Yeah, in this case, well, even when the researcher used built a kernel with this 45 version of memcpy enabled, that was really not going to prevent the vulnerability because the memcpy function, what it was going to do, it was going to return the size from the beginning of the array up to the end of the structure. So yeah, at the end, he was going to be able to corrupt that pointer in any case. So we had a problem. What we noticed at the time was that we had two main issues. We had the issue that This was very annoying to discover. This was, when we noticed that he corrupted this array, we were really angry about it because we were like, okay, but this information, the size of this object is known to the compiler, right? I mean, how in the world this can happen? How in the world is that we still have a lot of these vulnerabilities out there when the compiler can help us? And the other reason that we discovered is this case that, well, we were not using the right mode for this built-in compiler function. Okay, so what can we do about it? Well, we could just simply replace, right? Instead of using mode 0, we replace this with mode 1. And now, well, we are going to make sure that this built-in compiler function is going to return the actual size of the array. And then, well, if the vulnerability is not going to happen, right, in this case. So yeah, this is enough. This simple change was enough, or is enough, to prevent this kind of vulnerabilities. So that was a good thing at the end of the day, is we fortified, or we hardened the kernel a little bit more, right? And life is beautiful, right? Okay, but what about something that we call intentional cross-member overflows? Do you have an idea what that is? Okay, let me give you an example. In this case, we have a structure, and we have 3 objects, 3 arrays. And at the bottom, we have a memcpy. And what this memcpy is doing is, it is writing data across these 3 arrays at once. That is an intentional cross-member overflow. So intentionally, we are overriding this array, right? Because well, I mean, the developer, the C language is pretty flexible, right? It's probably the reason why it's so successful, but at the same time is its Achilles heel, that flexibility, because that allows for all sort of shenanigans, and if people get confident, they can actually code, they can actually hack their way into production. What that means is that they are not necessarily using good coding practices, they are just hacking whatever they need to produce in order to get the job done, right? And that is not uncommon, unfortunately. Okay, so this is an intentional cross-member overflow. And this is pretty valid code. This is valid code, right? Because we are trusting, and the compiler is trusting that the developer knows what he's doing, or what they are doing, right? However, if we change from mode 0 to mode 1, and we enable the fortified version of memcpy, what is going to happen here is that we are going to get a false positive. Because now the fortified version of memcpy is going to say, okay, well, the size of this object is actually, well, whatever it is stored in this macro, and you want to write across this object, you are overriding this object. So you know what? Here's a warning, or depending on the configuration under which you build your kernel, you're going to get a warning or a panic, right? And however, the code is correct. It's correct. So we need to do something about it. At the time, we discovered that we had a lot of these problems. Yeah.
Intentional overflows, is that why it was originally 0 instead of 1, the mode?
Oh, you're asking the reason why.
Why was it set to 0 to begin with?
Yeah, originally, yeah. That's one of the. That's actually one. That was one of the reasons, because when people were changing this code, they discovered that well, a lot of false positives were out there, and at the time, well, probably they didn't want to have the responsibility of going and addressing all those false positives, right? However, this is also the same was used in the fortified version of a few string functions, of a few functions that to handle strings in the kernel, and but that was one of the reasons. There is another reason that I don't remember at this moment, but yeah, I mean, yeah, because if you use mode 0, yeah, I mean, you are not going to see any of those false positives that we run into when, at the moment we change it for mode 1, right? However, this vulnerability was very annoying, right? And yeah, we needed to do something about it. Okay, so yeah, we have intentional cross-member overflows. So a solution for this is to create a substructure. In this case, we can just create a substructure. We enclose those objects. We create a new identifier for the compiler, and now the compiler, what the compiler is going to do is, okay, well, you are giving me a pointer to this substructure. Oh yeah, sure, you can do this because the size of this object is the size of these 3 objects, right? So that is a potential solution. The issue with this is that whenever we need to access any of these members, we need to go through this substructure first. So that pollutes namespaces, and that for a lot of people, that's what they call code churn. So they don't want to do that. They are like, okay, well, I mean, my lines of code are getting larger. I don't really want to do that. So yeah, that is one thing that we could do. Another thing that we can do, and that we did, was we created the struct group helper. I'm going to show you how this works. Let me just explain you how this works here quickly. Okay, with this new helper, now we can access each one of these members either directly or through the new identifier. So these 2 lines of code are equivalent and work the same, right? That is the magic behind struct group. So now let me explain you how this works. Okay, well, this helper was created by Case Cook. Case Cook is the mastermind behind kernel hardening. He is the leader of the Kernel Self-Protection Project. He's a Google employee. He's great. He's great. And Keith Packard, actually they are friends. they live in the same city in the States. Yeah, Keith Packard is another legend in the kernel community. So they both created this. They came up with this idea of creating this macro. Okay, let me tell you. This is actually a family of helpers. We have different helpers to do different things. Okay, so how this works is this. Inside, as you can see, well, inside we have a union, and we have an anonymous union. That's important, and we have an anonymous structure. And that anonymous structure is what allows us to access those members directly without having to use a substructure name, right? And also we have a name structure. And with the help of this name structure, now this whole group of members gain bounds checking in the eyes of the compiler. Because now the compiler have an identifier to refer to the whole group. So now at compile time, the compiler is going to know how big this group of members is going to be. And that is useful for bounds checking. Okay, so the solution for this intentional cross-member overflow is this. We use struct group, and we can even get rid of this line of code, because instead of manually calculating this, we can just apply the size of operator to the new identifier. Okay, so with this struct group, we fix false positives. Well, again, what happened then is, okay, now we had to identify all those false positives and fix that code, right? So that was, again, a lot of work, but that was work that we had to do. Otherwise, people were not going to accept that change to memcpy, because I mean, generally speaking, we don't like warnings, we don't like false positives. We are pretty picky in the kernel community, right? And that's for a good reason, because we are pursuing technical excellence. And that's something that you have to pursue, right? Okay, so, yeah, so in this case, well, yeah, we finally can use, just after going and taking a look at every false positives created by this change, just after fixing all of those false positives, is that we could actually have this code applied and accepted in the Linux kernel, right? And well, again, life is beautiful. of course. Well, this is always the case in kernel hardening. Okay, let's review. Let's take a second look at flexible array members. Let's see if we find something interesting there. Okay, this is just as a reminder. Again, when we use building object size, and we pass a pointer to a flexible array member, the compiler has no way of knowing the size of this object, right? This is just as a reminder for both, for mode 0 and mode 1. Okay, now let me show you how memcpy works when we want to write some data into a flexible array member. Okay, so at the top, well, we have a flexible structure, and we are writing some data of some size in the flexible array member. So this is going to be a walkthrough of the 45 version of memcpy. So what happens here is that, okay, building object size cannot determine, of course, the size of this object. Size t is of type, is actually an unsigned integer. So this is going to turn into a really big number. Actually, it's going to turn into the maximum number that an unsigned integer can store. So this condition is going to be false. So we are not going to warn about any possible write overflow because we don't have enough information really. And at the end, we execute memcpy. Now, all of this is expected behavior. This is how things were at the time, right? However, when we were playing with the 45 version of memcpy, and we were playing with building object size and trailing arrays and flexible arrays, we noticed something quite disturbing. We noticed that building object size was in fact refusing, and that is the word. This building object size was refusing to give us the size of any trailing array of any size, not only of a trailing array, not only of a flexible array member. So let's remember our function from the beginning, our structural function. So even in this case, when the compiler again knows exactly how big this object is at build time, even in this case, this building compiler function was refusing to tell us the size of this object. And that was like, yeah, exactly. It was like, what in the world? It was like, that was pretty annoying, disturbing. And yeah, again, we were like, oh my God, we thought we were making progress. Okay, let's find out what is going on here. Okay, so yeah, well, under this scenario, well, we not only are not able to sanity check or to prevent any out of bounds on flexible array members, we are not able to prevent any out of bounds or override in any trailing array of any size. Now, why? Okay, this is, there are historical reasons for this. This is a piece of BSD code. So what we have here, we have a trailing array of a concrete size at compile time. But in reality, at runtime, this array was behaving as a flexible array member. So at runtime, it can go from 14 bytes up to 255 in size. This is the reason why compilers were refusing to tell us the size of any trailing array, because they noticed, compiler people, they noticed that developers, C developers, they were using trailing arrays of any size as flexible array members, as a variable length objects. So they noticed that behavior, they noticed that kind of development, and then just said, okay, well, you know, chances are that you, at some point, are going to use this trailing array as a variable length object, so I better don't mess with that. So instead of giving you a concrete size, I tell you, I don't know. And it makes sense, right? Because they didn't want to mess with I don't know, probably millions of C code bases out there, right? that use this kind of code in practice, right? So well, this exemplifies a little bit of all the nuances that comes when you want to harden and to make the Linux kernel a little bit more secure. You run into all sorts of issues, into all sorts of problems. You have to go and talk to all sorts of people. We are in contact with GCC developers, with client developers. We in the Kernel Self-Protection Project, every other week we have meetings with them because, well, we work together to fix this kind of issues. And it's really interesting. It's really interesting. It demands a lot of work, a lot of dedication. Usually you get frustrated, but it's important work. It's valuable, and it's work that the world needs, really. Okay, so yeah, we got in touch with GCC developers, with client developers, and this is what they reply. They say, well, you know what? That's actually a feature, not a bug. So what are you talking about? So yeah, if you are curious about the whole discussion, of course, you are going to have my slides available, so you can go and take a look at it. You can read the whole thing. it might be interesting. So yeah, this is basically what they say. Well, you know, we noticed that this is something that people are doing out there. So yeah, this is the way it is. and the problem is that it prevents important building compiler functions like building object size and building dynamic object size that we are going to review this building function. It prevents these building compiler functions of working correctly, right? So yeah, that's an issue. That's a problem. Okay. So yeah, again, what can we do about it? What can we do about it? Well, it turns out that we could do a couple of different things. We could make some progress on the compiler side and at the same time on the kernel side. So when it comes to the compiler side, well, of course, that needs to be fixed. But that was fixed only after the introduction of a new compiler option, which is strict-flex-arrays. We are going to review how this works. With this compiler option, what happens is that we fix the ambiguity of having different ways of declaring a variable length object, right? So only after fixing that ambiguity is that this building compiler function could be fixed up. On the kernel side, of course, well, we need to get rid of, at the time, we started calling the one-element arrays and zero-length arrays, we started calling them fake flexible arrays, right? And yeah, so what we thought at the time was like, okay, well, we need to complete the work, we need to complete this work of transforming these fake flexible arrays into actual C99 flexible array members. With that, we remove the ambiguity, right, of having different ways to declare the same type of object. And that is useful because in that case, now the compilers, can properly reason, can know when we are actually trying to use a flexible array member, right? And of course, well, only C99 flexible array members should be used as flexible arrays. So okay, so now I am going to explain how this compiler option works. Okay, well, this was released back in GCC 13 and in Clang 16. And well, basically, well, the idea is that you can have different level values for this number. The strictest form is the number 3, which means that only C99 flexible array members are going to be considered by the compiler as variable length objects, right? Now, let me give you, a little bit of the history of why it is the case that we needed different level values. Again, there are a lot of code bases out there, C code bases out there, that they use one-element arrays and zero-length arrays, and they cannot afford to have a group of people, a group of Google employees, a group of hackers, a group of senior developers fixing their code base. So they are going to remain with those issues, right? So in those cases, well, they can start making progress. Probably they can start addressing zero-length arrays. And if they address the problem of zero-length arrays and they only use one element arrays in flexible array members as variable length objects, well, probably they can use, instead of 3, they can use level value 1, right? That means that, well, okay, you just fix the problem with zero-length arrays. And if you, probably number 2 means that, okay, you now fix the problem with one element arrays. So it's a way to give them the option of making progress, of fixing their code base, right, progressively. So that is actually the use of these different level values. In the kernel, well, we want the strictest one, right? We want to get rid of any ambiguity. So this is the level value we use, number 3. And okay, well, this is how this works. If you under this level value, if we pass any non-flexible array, well, this building compiler function is going to return the actual size of this object. This means that if we use a one element array, it is going to return the size of that one element. If we pass, as in this example, if we pass a zero-length array, well, it's going to return 0. So yeah, so with this, well, all those training arrays of fixed size, now they gain bounds checking. By enabling this compiler option and fixing this building compiler function, now we remove that ambiguity, and all those training arrays of a fixed size, they gain bounds checking, right? And well, this was enabled in Linux 6.5 a while ago, and yeah, so that ambiguity is gone now. Again, we gain bounds checking on training arrays of fixed size. Okay, but what about bounds checking on flexible array members? In the Kernel Self-Protection Project, we are ambitious. We really have a passion for working in the kernel and doing whatever we need to do to secure this important code base. Because it's, I mean, the Linux kernel is ubiquitous, right? And it's really important for the digital infrastructure of the world, right? Yeah, so for that, we had the idea of this attribute, the counted by attribute. This is out there in GCC, in Clang 18, and it is about to be released probably in April next month, according to the development, to the development cycle of GCC. Apparently, they are going to release GCC 15 in April. Okay, how this works? Well, what's going on here is that we can, through this compiler attribute, now we have a way to link or in some way relate the counter member to our flexible array. So this is actually how you annotate a flexible array member. You use the counted by attribute, and you are going to pass the name of the member that you are going to use as the counter member. So with this, the compiler now has an idea, or at least it is going to know where it has to go and look for the size of the flexible array member at build time, at runtime, I'm sorry, right? And well, this is how this works. It points to the struct field that holds the number of elements our flexible array member is going to contain at runtime. And well, with that, well, again, here is the, it is interesting. I mean, if you're interested in this, in the kernel, and you are, in this presentation is being interesting for you, it doesn't hurt if you go and read as much as possible, right, about this. So here's a link where you can take a look at it. So yeah, it is going to help us to improve bounds checking on trailing arrays. Now, instead of using building object size, we are going to use building dynamic object size, right? And well, of course, in the kernel, we have helpers for everything. We have macros for everything. So if you go and take a look at the kernel code, you are going to see something like this, right? So instead of the raw attribute and the counted by and all that thing, well, we enclose that in a helper, the counted by helper, and you just use it like this. Okay, so now the next thing that we started, the next word that we did was, okay, we started looking for all those instances of flexible array members, and we started annotating them with the counted by attribute, so that all of them can gain bounds checking at runtime. Okay, so now another thing that we had to do, we had to replace in the 45 version of memcpy, instead of using building object size, we needed to use building dynamic object size. So we replaced building object size with this building dynamic object size, right? And at compile time, it works exactly the same as building object size. So, but this adds the benefit of providing around runtime bounds checking coverage on flexible arrays. And yeah, so yeah, these are runtime bounds checking coverage. If you build your kernel and you enable this flag, you are going to gain this level of fortification. So you can play around. I don't know, have you ever built the Linux kernel? Never? Well, probably this is a good opportunity for you to go and take a look and experiment with that. It's really interesting. I mean, you can learn a lot about security, about how to write firmware, how to write drivers, and yeah, and I mean, companies, they are always looking for kernel engineers. So yeah, so with counted by and building dynamic object size, we gain bounds checking on flexible arrays. And that's really an amazing thing. A few months ago, the last year, I wrote a blog post on how to use the counted by attribute on NEC codebase out there. And I use examples, of course, Linux kernel code. And well, you can take a look at my blog, and you're going to find a blog post there. It's quite complete. However, the syntax is about to change. I'm not going to explain that in this presentation, but most of the things I talk about in that blog post applies. Okay, so yeah, the next thing that we did, well, we modified memcpy, and now we are using building dynamic object size. So yeah, well, up to this point, I've been walking you through to the evolution of bounds checking in the Linux kernel. So this that I have presented here has taken us years. It's years of work. Yeah, 6 years of work, 5 years of work, right? And we continue doing this work because we continue, GCC developers, client developers, compiler people, they continue improving counted by, because now, well, let me tell you this. The reason why the syntax is going to change is because we became more ambitious, even more ambitious, and we had the idea of, instead of just using counted by for flexible array members, we said, okay, well, what if we use this for pointers? And now compiler people, they are developing this. So yeah, we are about to have bounds checking on pointers, thanks to the use of this counted by attribute. This is what's coming next. So, oh my God, it's a lot, right? Yeah, okay, well, this is the last part. This is something I've been working on. I started working on this actually in late 2023, and all 2024, all the last year I've been working on this during the last year. Okay, well, this is a new compiler option. Wflex-array-member-not-at-end. This was released in the last version of GCC. And okay, what's going on here? Let me explain this to you. Okay, well, what we have here is, let's remember that one of the requirements to use a flexible array member is that it should be the last member in the flexible structure. And well, the reason for that is because we cannot have another member after our flexible array member because we don't know how large the array is going to be, and we are going to, chances are that we are going to override any adjacent members, right? So that is one of the reasons why we should not use, and the compiler won't allow you to use or to place another member after a flexible array, right? However, well, it turns out that we run into a lot of cases where, yeah, people had their flexible structures, but then they were declaring objects of the type of a flexible structure in the middle of other structures. So what happened? That again is undefined behavior, right? Because you don't know how large your flexible structure is going to be. So the moment you write into your flexible array member through this new object, you are going to override. Yeah?
Does that mean that structs are limited to only one flexible array member?
Yes. Yes. Yeah. I mean, however, there is a case that sometimes people, they need to use multiple flexible array members, but they cannot go one after the other. You can do that as long as you use a union. Because when you use a union, all the members that you include in the union, they are going to share the same memory layout, right? So yeah, that is possible as long as they are in a union, but not one after another. Yeah, good question. So yeah, okay, so in this case, what this compiler option does is that it detects all these cases. It detects the cases where we have an object of the type of a flexible structure in the middle of another structure, right? And we need to fix it because this is an issue, this is a problem. I mean, now, there are a lot of course, a lot of kernel developers that they are very senior developers and they know what they are doing. However, I have run into, I don't know, between 3 and 5 actual bugs detected, right? In this case, that they were, we had a flexible structure in the middle of another composite structure. The developer, they didn't notice that, and we had actually memory corruption issues, bugs. So yeah, this is something that we want to fix. So I am working on this problem, and let me show you this. When I enabled this compiler option and built my kernel, I got 60,000 warnings. And this is typical in kernel hardening. We have thousands, hundreds of false positives. Of course, the vast majority of these warnings are false positives. However, only 1% of those are unique issues, right? The reason why we have thousands of warnings is because, well, this code is in headers, right? And headers are included in hundreds of C files. That's the reason why they multiply, right? But it comes down to like just about 1% of the total number of warnings, right? However, 600 warnings, 600 issues to fix is a lot. So yeah, so this is the problem. So, okay, well, I went through some of these hundreds of unique issues, and I classified those into 4 main categories. So this is actually this is code upstream. This is code in the Linux kernel upstream. So you can take a look. You are curious. Well, you can take a look at the commits, and you can read the code, and you can read the changelog text. Hopefully, it will make sense. And yeah, so let me go just quickly through each one of them. The first case that I noticed is when, well, the flexible array member was actually never used. It's like people, at some point, probably it was used, but then the code evolved and they made some changes and they forgot about it. And it's just like a leftover code. And the solution there is simple. We just remove the code and that's it, is not a major problem. Case number two, well, in the case number two, people, they actually not using the flexible array member. We don't have the problem of corrupting data or members in the composite structure because all what people needed was to access the other members in the flexible structure. So they were not messing with the flexible array member. They just didn't want to create like another separate structure with just the header part of the flexible structure. They just said, well, in the end, we are not going to use this object. The size of this object is 0. Yeah, let's just declare an object of this type and use the rest of the members. Right? That was that's another case. However, we need to fix this because even when most of these cases are false positives, we need to make sure that we don't introduce unintentional issues, unintentional bugs, right? The third case is probably the most complex one and the most interesting one. What happens here is that in the composite structure, if you notice, we have a fixed size array just after this object of the type of a flexible structure, and the element type of this fixed size array is of the same element type of the flexible array. This is interesting because this means that people, they knew, well, under certain configurations and under certain circumstances, of course, they knew how large the flexible array member was going to be at runtime. So they allocated space for the flexible array up front. Yeah, and the thing is that now they have enough space to iterate over the flexible array in a controlled manner. This is a hack. That's what I was referring at the beginning when I was saying that people tend to hack their way into production, right? They abuse the flexibility of the C language. But again, it's interesting. So yeah, this is the most complex case. And yeah, fixed size, the flexible array and the fixed size array, they share the same memory layout. Because they share the same address. It's like having a union. But yeah, they form an implicit union. Okay, so yeah, the last case is basically the same as case number 3, an implicit union, but on stack, right? So again, we have a flexible structure, our flexible array member, and on stack we have our fixed size array. And well, these are some, if you are curious, you can take a look and you can read the code. And it's interesting because here I am using some helpers that I didn't mention in this presentation, are interesting helpers. I mean, if you take a look at the kernel code and you read the helpers that people use, you are going to learn a lot because you are going to find out, okay, well, what is the reason for this? Oh, okay. Yeah, it makes sense because when I read this helper, now I know why people are using an anonymous union, why people are using an assert. You learn a lot while reading kernel code. So I recommend you, if you're interested, go and take a look. And well, yeah, this is a link actually. You can click there and you can see all the patches I have sent to address this problem. Okay, so now after sending like a couple dozen of patches, well, a little bit more, like probably 3 or 4 dozen of patches, I managed to go from 600 down to about 300 of these warnings in the kernel. So I'm done like I completed half of the job, right? And that accounts for like about 20,000 of total warnings. So yeah, well, some conclusions because I don't know how long it's been taking this. Okay, so we had the problem of unintentional cross-member overflows, you know, the bad vibes like bugs. Okay, that is fixed by updating memcpy to use building dynamic object size in mode 1. Okay, after that, well, originally we didn't use building dynamic object size. We used building object size, but at the end of the day, this is the final state of memcpy. Okay, so then after that, well, we run into the problem of intentional cross-member overflows. Okay, the solution for that was the implementation of the struct group family of helpers, and we had to go and fix tons of false positives, right? Then, well, we had the problem of the ambiguity of having different ways of declaring a flexible array member, so we call that the training array ambiguity. Okay, that is fixed by transforming every instance of fake flexible arrays into C99 flexible array members and enable this compiler option, right? Then, well, we run into the issue, okay, well, we fix the problem of bounce checking on trailing arrays of a fixed size. Okay, now what about flexible array members? Okay, the solution for that is the creation of the counted by attribute. And of course, with this, we use building dynamic object size. And yeah, we've been doing, this is still work in progress, actually. I mean, we continue annotating these flexible structures because there are a lot of nuances with these transformations. Then we had the problem of the flexible arrays in the middle of composite structures. Okay, well, the solution for that is, well, we need to enable this compiler option. We need to clean up a lot of code. We need to refactor a lot of code. That is work in progress. If you're interested, take a look at the commit IDs. So some conclusions, more conclusions. Okay, well, we have a clear strategy on how to address this last part of the whole thing, how to address these flexible array members in the middle. You build your kernel with config UV bounds and fortified source. You are going to gain all this fortification that I've been talking to you here. So it is, it'd be a good practice if you experiment with this. Probably you can even propose some patches. That'd be amazing. And well, finally, well, I want to think that we are improving the security of the Linux kernel. And with that, thank you. Thank you guys, thank you.